Hello everyone, this is Wilson Hong. I'm from Moldex3D EMEA. So for today's topic, we're going to talk about a new function in Moldex3D 2020. The function is called to consider the ejection timing after mode open. So I will demonstrate you how that can be achieved. So let's get started with the slides. So you can see obviously that from left to right, this is a molding process. And you can see that in the beginning, we are in the filling and the packing stage. So in this stage, mold is totally closed. So heat can be dissipated, can be transferred from the part to the mold directly. But after EOC, after the end of cooling, the mold will start to open. So when it is opened, one side of the part will be in direct contact with the air instead of the mold. So we will have a different heat transfer condition on the left-hand side and right-hand side of the part. And after the end of cooling, then after the ejection, part will be ejected. So part will leave the mold, so the part will be staying totally in the air. So the heat transfer condition will be just the air surrounded by the part. So in the simulation, in the old ways, we can only simulate it when it is after EOC. We will assume that the part will be placed instantly to the air. So the part will be surrounded by the air. So we got this kind of heat transfer condition. But in the new feature in 2020, we will be able to consider that how long the part will be last in the mold instead of ejected right after EOC. Because in reality, this of course happens. So you can see that on your right-hand side that there's a interface, the screen clipped interface that you can set the time for the after the mold is open and until the time the part is ejected from the mold. So let's look at the real example. So here I prepared a model. So this model is like a cap, a bit like the PET bottle cap. So you can see that this is a cap, and we got a hot runner. This is a very simple model. We got a very short hot runner on top of it, and surrounded by the cooling channel. Okay, and to do this kind of analysis, we will need to build up the mold plate. So in the old ways, we can only build the mold by things like mold inserts and also the mold base attributes. But right now we have a new attribute called mold plate. So mold plate can be separated into two different parts. One is the mold plate movable one. Another one is the mold plate, the fixed one. Okay, so you can see that this is the fixed one. So to prepare this kind of analysis, you will need to prepare two sides, the mold plate, and of course, if you've got mold insert, you can have them, of course. And I will show you that roughly what kinds of file we will need. The list. So we got a cooling channel, which is made by a 3D model. And also we need the mold boundary, the mold plate with the fixed side, and also the mold plate, the moving side, and then the parts and the hot runner. But for the mold base, this is not necessary in this analysis. If you have mold base, you can only do the cool analysis in the old way. Yeah. So we need to define the mold plate. So the full model will be like this. We have the part in direct contact with the mold plate, and the movable one, and then the fixed one. Then we have the complete model all together. So this is everything. Yeah. Okay, so after you finish this model, like the node seeding, and you generated the solid mesh and everything is completed, and you save the mesh, then you pick up the material you use for this process, then we should go into the process setting. So I will show you briefly how we can set it. So originally we have only the mold open time setting. So by default like 5 seconds, and by default the ejection timing after mold open is 0. So we can choose how much long the part will be staying on the mold after the mold is open. So let's assume like 1 second or 2 seconds, maybe 2 seconds for it to stay, and after 2 seconds the part will be ejected from the mold, then it will be placed in the air. So we got a heat transfer condition in the air. Okay, so this is it. We set 2 seconds out of the 5 seconds of the total mold open time. Yeah. So I will show you how the result will be like. So I created 2 runs. Run 9, this one is the old way. So the part will be ejected right after the mold is opened. But for run 10, I set like 3 seconds for it to stay on the mold after the mold is opened. So let's see. So I got 5 seconds for the mold open time, and I got 3 seconds out of 5 seconds for the part to be staying on the mold, which is more realistic, of course. Then we will see the difference. So the part will be staying on the movable side. Let's see the movable side. The mesh of the movable side like this. Okay, so part will be staying here. Movable side. So we are expecting that the part will be colder on the movable side when it needs to stay longer on the side. So let's do a comparison for the 2 runs with or without this kind of condition. So we'll turn off all the mold and leave only the part to check the temperature. And I'll use the compare to sync the angle, the results, and also sync the range, so you can see easily how the temperature is different. So on the one side, on this surface, this is the fixed side. So for fixed side temperature, they are quite alike, a little different, but not too much. But you can see on the other side, this is the movable side. You can see that on the right hand side, that run 10 is the one that we use the delayed ejection phenomena calculation. So in this model, you can see the temperature is lower on its on the movable side, and this one got higher temperature because this one stays 3 seconds more in the mold in comparison to this one. So this one is in direct contact after it is ejected, after the moment of EOC, the end of cooling. Yeah. So that's roughly how this kind of analysis can be done. Very easy, and so I think that's it for today's talk. Thank you for your attention.